So it's about time, and let's get started. Good morning, everyone. It is my great pleasure to welcome you all to today's seminar, hosted by the Institute for Future Initiatives at the University of Tokyo. My name is Masa Sugiyama, and I will be moderating this event. It is our great honor to have Dr. Luis Sarmiento from the Central Bank of Mexico with us today. Dr. Sarmiento will be presenting on the topic comparing decarbonization scenarios across the Atlantic with the American and European energy modeling firms. His talk is based on a large-scale project that explores long-term strategies and net zero goals for both the United States and the European Union. This presentation is particularly relevant to the ongoing policy debate within Japan, and we are now trying to update our nationally determined contribution and the basic energy strategy. So this is indeed very relevant and interesting. Dr. Sarmiento is an environmental economist with extensive expertise in applied econometrics, causal inference, integrated assessment, energy, and agent-based modeling. We are fortunate to have him share his insights and findings with us today. This seminar is part of the JST Social Scenario Research Project, which aims to contribute to the realization of a carbon-neutral society in Japan. The project emphasizes sustainable development through science and technology and envisions a desirable future society by exploring pathways, options, and strategies to achieve it. Since April 2023, last year, the project has expanded to integrate knowledge from a broad range of researchers, including those from humanities and the social sciences, fostering further development and social contribution. I have a few housekeeping announcements. So to ensure smooth experience for everyone, we kindly ask everybody to keep their video and voice off during the seminar. I think you just can't turn it on, but please keep muted. And also if you have any comments or questions, please use the Zoom chat function. It's available to you. So yeah, please do so. And you can raise your questions during his presentation. And this seminar, it will be recorded, and also I think it's already being recorded. So without further ado, I would like to give the floor to our speaker today, Dr. Luis Sarmiento. So please join me in welcoming Dr. Luis Sarmiento. Thank you. The floor is yours, Luis.
Thank you. Thank you very much, Professor, for that very kind introduction and also for the invitation. I'm very excited to be here. I think we as climate scientists and energy scientists, it's very important to do networking and to understand what is happening in other regions in the world. And this is kind of the inspiration for this paper, because sometimes you get the grants for your country, you do the research for your country with very specific policy agenda or a very specific framework, and you miss a little bit of everything that is happening out there, right? So well, without further ado, let me share my screen. I hope I don't have technological problems, as it is often the case. Give me a sec. Okay. There we go. Masa, can you see the presentation?
Yeah,
everything
it's perfect. Yeah, thank you.
Okay. As Professor Sugiyama just said, I'm going to present a recently published paper. The paper was published in Energy and Climate Change, and it's part of the special issue of the Energy Modeling Forum 37. The title is extremely long. It's this Comparing Decarbonization Scenarios Across the Atlantic, blah, blah, blah. I think it's the longest title I've ever worked with, and also this is the largest amount of co-authors I've had. And this is because it required a large amount of coordination of all of the energy integrated assessment models and energy models that participated in this research. Although Professor Sugiyama already said, I'm going to do a little bit of introduction about me because there's a lot of time to cover. I'm an economist by training. I think that's interesting because in the integrated assessment modeling world and also in the energy modeling world, I think there's fewer and fewer economists with time. It's becoming an engineering specialty, and I think it's important to have both economics and engineering. My PhD is from the Berlin University of Technology, and I'm currently affiliated with the Euro-Mediterranean Center for Climate Change. And I'm a research economist in the Bank of Mexico, and I'm just going to join the Bank of Mexico this month, and I'm going to work in these topics, in climate-related topics, environmental topics for the central bank, which is good news for everyone in this call, that the central banks are already interested in what we do after a couple of decades of doing it. My strengths, funny enough, is applied econometrics, spatial econometrics. I'm a more traditional economist dealing with micro-level issues. However, I've also specialized in energy modeling and integrated assessment models, and this was just a matter of chance. I think it was 2018, 2017, that while I was in Mexico, my supervisor, Christian von Hirschhausen, was invited to the Energy Modeling Forum 34. And he couldn't come from Germany. And he said, you're in Mexico, go and represent me. And I met the entire community. I met what was integrated assessment modeling, what was energy modeling, and I was happy to contribute. So I have already 5 to 6 studies, and I constantly work with John Wyand and the Energy Modeling Forum in this type of topic. So this is kind of half of my research goes into the direction of this kind of models, and especially the presentation that I'm going to do right now. So to be very, very specific and very broad, what did we do? And the idea is that this paper was mostly, I wouldn't like to call it a scientific exercise, but it was a coordination exercise of a lot of little scientific exercises, because in the end, every energy model, every integrated assessment model is a little scientific exercise of a team of researchers in a certain part of the world, right? And the idea of this paper was to coordinate them all and try to see the results of all and see if there were differences, both between the European and the American models. So I have the advantage of being participating in the Energy Modeling Forum 37 in the US. This is the 37th year that they do it. So it started in the 70s, led by John Wyand, and they have been doing it constantly. I'm sure most of you are familiar with it. And Europe is just catching up with this European Climate and Energy Modeling Forum. It was funded by the European Commission, and the intention was just follow the example of the Energy Modeling Forum, but with European teams on European topics, because the Energy Modeling Forum is mostly dominated by North American teams. So once I talked with John Wyand and I told him, hey, let's use the results from the European Energy Modeling Forum and from the American Energy Modeling Forum to try to compare the decarbonization pathways of both regions and try to see if there are differences between the modeling teams. That the initial intention was to see if European modeling teams have a different set of assumptions than American modeling teams, and to compare if there were some biases that were there for any of both regions, right? You can think of European models using carbon prices way before than American models because, well, they have the ETS way before the American models. That was the intention, but of course, most of the time was spent coordinating. As you can imagine, coordinating 14 modeling teams, trying to see the results, see if any of them made any mistake, and kind of have a conversation with them. In case their results were very different from the other models, ask them, is this because your model broke or there was something bad with your model, or is this just because this is what your model says, right? Which is also very important. So that is what we did in a nutshell. No, don't worry, the next slides have a little bit of more graphs, of more color. So the motivation was very simple, right? If you can see here, we have 2 plots. You have the share of cumulative and current cumulative emissions in the left side and contemporaneous emissions in the right side. And as you can say, United States and Europe, both in cumulative terms, are the 2 regions that has emitted the largest amount of greenhouse gases to the atmosphere. And this is just because of a consequence of early industrialization in both regions. I think Japan is also an example of early industrialization, and I think also a relevant emitter, historical emitter. And even in contemporaneous emissions, even with the rise of Asia, the rise of China, and the current ongoing rise of India, the European Union and the United States are still a relevant part of world emissions. We are talking around 23, 24%. And it was not only that, talking with John Wyand, it was not only focused in these regions because they have polluted a lot, but focus on these regions because very likely they're going to be the ones leading the transition towards the net zero, especially Europe and the US, because they are wealthy economies and they have the resources to try to push the technology in order to reach net zero, kind of to shift the technological curve of a lot of these technologies. I think Japan is part of that idea. At the start of this conversation with John Wyand, a discussion was about contacting MASA or contacting the Japanese teams or some teams in Asia in order to make a global intercomparison exercise. But simply the coordination cost already with these 2 different modeling forums and these 2 regions were very high. And in the end, we didn't manage to coordinate effectively. But the idea will be eventually to start also working with teams in Asia. And of course, hopefully with teams in Africa, and teams in Latin America, which they are more scant in order to make a more robust exercise. Well, the goal was very simple. It was compare the net zero pathways of both regions. And you will say, well, this is not extremely interesting. There's so many very interesting papers already doing this. What are you bringing to the table? And what we're bringing to the table is this massive coordination that we did, in which we have access to 28 different models with very similar assumptions, which is often not the case. Often either you have just one model and you study the effect of one model, two models, perhaps 5, 6 models in some papers. Having this wellness of models was kind of the differentiating part. So we start, we have the European Union and the US. The definition of each model, as you can imagine, is a little bit hectic. Some models included the UK as part of Europe. Some models didn't. Some models included Turkey. Some models didn't. So it was also a bit chaotic to define what were the regions. 9 models participated in the study effectively, meaning that these modeling teams were there writing the paper, helping in data analysis, running specific scenarios, right? And these are like teams that you might know. This is GCAM, this is WICH, this is IMESH, ECMSMER, that is part of the Canadian Environmental Agency. And these were just 9 models in the cross study. But besides these 9 models, we have access to all of the results of the energy modeling forums of those models that didn't really participate, right? So for example, for the US, we have 14. So besides the 3 models that participated effectively, we have access to additionally 11 other models with 11 results for net zero scenarios. And these go from US region, TEMWA, GTEC, several models, both integrated assessment models and energy models. And for the European Union, we have other additional models like PRIME, SOSEMBI, MISA, EuroCalliope. So as you can see, we have a wealth of modeling, of model results, and this was the challenge, to coordinate all of these model results and to make a sensible story around all of their results. Very likely in the future, we will make more stories because we have access to all of these results, and we will try to see something interesting going on there. But this was kind of the first attempt in order to do something. Give me a sec. I want to open the chat and put it in one corner in case anyone asks something. If anyone wants to ask something, just go ahead. So what we did, so first we said, okay, we have a lot of coordination issues. We can, as you increase the amount of models in an exercise that are going to participate, you have to decrease the amount of scenarios, because the likelihood that one of the modern teams will not be able to run a scenario or is not going to have time to run a scenario gets higher, right? So we decided, let's keep it as simple as possible. We want to analyze a national policy scenario and a net zero scenario, right? It's very straightforward. What were the homologizing assumptions? And there are very few of those. We wanted the teams to be as free as possible, right? So the first thing is that in both in the net zero scenario and the national policy scenario, we assumed carbon sinks. And these carbon sinks come from land use and land use change. We assume 310 million tons for Europe and around 800 million tons for the US. And these are in line for the US with estimates from the Environmental Protection Agency of the carbon sink, and for Europe from the European also the Environmental Agency of Europe. And these are homologizing assumptions in both national policies and net zero scenarios, these carbon sinks, right? Which help a lot of models to reach the net zero. Then we also have in the net zero, then we have 2 differences. We have net zero CO2 emissions for the USA. This is the first assumption. And then net zero greenhouse gas emissions for Europe. And the first thing that you will think is, why do you have net zero CO2 for the USA and net zero greenhouse gas emissions for Europe? And this was a consequence of both forums. So both forums work independently. In the American Modeling Forum, I was there in the meeting in 2022. We were deciding, are we going to do net zero CO2 or net zero greenhouse gas emissions? And the decision was net zero CO2 because the White House, all of their targets were based on CO2. And it was decided that it was more policy relevant to talk about CO2 in the US. Although we talk about the CO2 in the US, in the main paper of the Energy Modeling Forum, some teams did the greenhouse gas net zero constraint, and it was kind of around an increase of 5%. in the net zero. So instead of reaching net zero, you reach around minus 100 million tons. And for Europe, it's the same intuition, right? The European Climate and Energy Modeling Forum decided to go for net zero greenhouse gases because all of the European policies at that time were targeting net zero greenhouse gases. So all of the results that I'm going to give you, you have to take in mind these differences. However, the net zero greenhouse gases for Europe only decreases the net zero CO2 by around 5%. But keep this in mind. This is in the net zero scenario. So we have this net zero constraint for both regions, right? And in the national policies, what we did is that current policies, technological pathways, and everything depend on each team. And the idea is to leave teams as free as possible in giving us their results in order not to, because if you force all models to have the same technological pathways, the same policies, very likely you will end up with the same results, right? But we want the models to have different assumptions to try to understand what is the range of possible scenarios that our optimizations are giving us, right? So the models are free, and also there are no restrictions to CO2 or greenhouse gases in the national policies in the scenario. And finally, the last assumption is in the net zero, we have a global peak budget constraint of 650 gigatons of CO2 from 2020. So the idea is that in the net zero scenario, we are also going to cap the amount of CO2 that the rest of the world is emitting. And for the national policies, there was no constraint. It really depended on each modeling team. As you can see, it's a very straightforward two scenarios, not very complicated. And the idea of doing this was because we have 28 modeling teams that we want the results to be as sensible as possible, and we want to have the most results as possible. So these two scenarios were designed with that intention. Okay, so let's see the first graph, and this is just a preliminary result. It's nothing fancy. This is the average net emissions time series. This is not gross emissions, right? This will be everything we emit versus everything we capture. And what I'm going to show you here in the left panel is Europe, right panel USA, and then you have in this kind of dark purple the national policies scenario, and in the green the net zero scenario. Let's say the ribbon that you see will be the maximum and minimum values of each model. So this is kind of the range of results, and the not dashed line, the continuous line, that will be the median, and the dashed lines will be +1 and -1 standard deviations, right? So the first thing that you can see the first thing that it was nice for us is that there's a difference in emissions in 2020 between the USA and Europe. That, give me a second, let me minimize this. That says that American emissions are way higher than European emissions. Well, not way higher, but it's kind of a ratio of 100 to 80. And it was very nice because this is in line with the emissions database for global atmospheric research of the European Union, because there has been in the past complaints of some integrated assessment models on energy models with very different levels or very, very nonsensical levels of emissions in 2020. So then you cannot really trust the future scenarios, but apparently here, at least the median model is sensible. Then what we have is that on average, all models reach net zero, as you can see. Of course, you have a steeper decarbonization slope in the US, and the steeper decarbonization slope is just a consequence that the US is emitting way more right now. So you have a reduction around 22% in the US versus 18% per annum in Europe. And regarding the MPA scenario, like following current nationally determined contributions, current policies, the models estimates a decrease of 35% in emissions in Europe and 14% emissions in the USA in the national policies scenario. It is important to notice that when we run these experiments, the simulations, this was before the introduction of the Inflation Reduction Act. So the Inflation Reduction Act is not here. It was a state of the world in which the US had very few climate policies. There's an exercise part of the same special issue of the Energy Modeling Forum in which they integrate the specifications of the Inflation Reduction Act, and they do see decreases very similar to Europe. I mean, around 35% of emissions. So with the Inflation Reduction Act, this MPA scenario for the USA will look more attractive. But then what you might be curious is not the aggregate. I guess what you want to see, you show me net emissions, but where are these negative emissions coming from? And are they coming from the same places in Europe and from the same places in the USA, right? So here what we do is that we put all of the models in the x-axis, so you will see the usual suspects, GCAM, image, which, message, all of the usual suspects. We have the emissions, positive emissions, which will be mostly from energy and industrial processes. And then you have the negative emissions, right? Now, from negative emissions, we have a lot. We have, for example, BECS, so bio-CCS, fossil fuel CCS, direct air capture, land use change. So we have a lot of negative emissions. The technologies for negative emissions, each team has different technologies. So some teams, for example, didn't have carbon removal geological storage, while other teams have them, but this is kind of part of the interesting exercise that we're doing, right? So carbon sequestration in Europe, we will have, if we want to reach net zero on average, we will have to capture around 1,180 million tons of CO2, right? So capturing and removing is very important. And this capturing, 30% will be done with BECS, 20% with fossil fuels, carbon capture and storage, 19% with DAC, and 13.7% with land use and land use change. For the USA, it's a little bit different. For the USA, we have they need to capture way more, 1,860 million tons. However, for the USA, land use and land use change is a way more relevant tool. And this is just because of the characteristics of the continents that allow the USA to capture a lot of the emissions with this land use and land use change. The next following technology that is interesting for the USA will be BECS, DAC, and fossil CCS. So as you can see, all of the models, there's no exception. All of the models to reach net zero, they use these technologies. And as you know, a lot of these technologies have not been developed. So the question is, when are they going to be developed? Will they be economically feasible? And even if they are, what will be the consequences of implementing these technologies, right? We already have high emitters trying to use these technologies to kind of excuse their emissions, to say, you know what, we're gonna invest in direct air carbon and we're gonna keep emitting. So in the moment that these technologies become economically feasible, we also have to study what will be the reaction of the economy. But this will be a problem for future us, I guess 5-10 years down the road. But something just to keep in mind, we do reach net zero, but to reach net zero forcibly across all models, we do need carbon sequestration and carbon removal, right? Then what we did here, what I want to show you are the results, the kind of the heterogeneity of results of each model, of all of the models. So here what I plot is gross, net, and capture emissions time series. Here is for Europe, for example. The left column is the national policy scenario. The first row is gross emissions, right? The second row is carbon capture and storage and carbon removal. And the final row is net emissions. And the idea is for you to kind of see all of the possible results that the models are giving us and the heterogeneity that we have in the results. For example, you see this little blue line, this blue line over here. These are the emissions from message. And message, this team for the USA, doesn't have a region called USA. Message has a region called North America that includes Canada and Mexico. And there's no way for message to separate this region, right? It will involve a lot of work. So for message, this is actually North America and not the USA, right? Then you can also see, for example, for TIAM, you have here in carbon capture and storage and carbon removal and in net emissions, a very, very strange, or very, not strange, but different from the other models, behavior, in which carbon capture and storage increases heavily around 2035, then stabilizes and then returns to zero. And then, of course, this was conversations with the modeling team, asking TIAM, is this a typical behavior in your model? They told us, yeah, this is a typical behavior. Apparently, their model needs to develop all the technologies before and invest before. So they said, these are the true results of our model. So with this exercise, you can see, okay, there's a very nice consensus across both models about how net emissions and carbon capture and storage will look in the USA, with only the exception of TIAM, while in Europe you have way more agreement, although you can see some clustering, right? For example, here you can see some models that report lower gross emissions than other models in Europe. And this is discussed in the paper, right? So if we see the net emissions for Europe, the median team reports carbon dioxide emissions of negative 145 million tons. And this negative happens because we have net zero greenhouse gases, not net zero CO2, right? So we reach the negativity in Europe, while for the US, the median team indeed is reaching the zero, the net zero. So as you can see, when we receive this is the most clean version you can imagine. The first time we received these results from all of their models, they were results all over the place with values that made no sense. Very, very strange results. So it was a lot of work to send emails to the teams, to talk with the teams, to show the results to the teams and tell them, hey, you are deviating here. So this was most of the work in this paper, which I think this type of papers should occur more often. But once I went through hell, I understand why they're not so common. Okay. I'm sorry, I didn't move this slide. So 2050 gross median emissions decreased by 68% in Europe and 73% in the USA. So these are the gross emissions. And then the clustering that I was talking about, and regarding net emissions, all teams roughly hit the net zero target in both the United States and Europe. So good news, like all teams managed to reach net zero. Locally, there was no team that just broke. So no team, I remember in the energy modeling forum 34, there were already a lot of teams that couldn't reach net zero because just the model didn't give enough to reach net zero. Now all teams reach net zero, of course, making use of these technologies. Correct? Now, if we're talking that we're reaching net zero, I think the natural question of a lot of you is, well, what will be the carbon prices in a world with net zero? How is this translating to carbon prices, right? So what I do here is that I just show you the carbon prices in Europe. This will be the left-hand side, will be the national policy scenario, meaning without the net zero constraint. And then you have the net zero constraint on the right-hand side. This kind of bar plot is just the median and one standard deviation across the models that reported, right? So for example, here for Europe, in European carbon prices in 2050, they have a median in the MPI scenario of around $45, right? Although you can see some spread in models, you have some models reporting around $160, some models reporting no carbon price, but on average, all models, the median is $45. This median is not so informative. What is informative is the change when we put the net zero constraint. So the median grows from $45 to around $553 across models. Of course, also with a lot of heterogeneity, right? You have, for example, image over here that is reporting a carbon price of 1,423, while the lowest is reported by GCAM. On average, something that we notice is that American teams tend to report way lower carbon pricing than European teams. And this was one of the only insights when it comes to differences between the modeling teams of both regions. For example, I think this is even clearer for the USA. Here you have the USA. This is the national policy scenario. And then you have here the median carbon price. And for the USA, in the national policy scenario, the median carbon price across models is pretty much zero. But something that is interesting is that you do have some teams showing a carbon price, and all of these teams are European teams. So all of the teams, like this is already a difference in the modeling assumptions, meaning that European teams cannot model a world without carbon prices in the USA, and they have to impose carbon prices. And this is because Europe has the ETS for almost 20 years now, right? So they are used to thinking this carbon price kind of idea. While the US, well, they have some carbon price initiatives, but overall it's inexistent. Then when we move to the net zero in the USA, as you will expect, the carbon price increases and it's for around $410, right? This has, as with Europe, some heterogeneity. For example, Markall reported 1,477. I sent several requests to that team, and they told me this is their true value. They cannot reach net zero with any other carbon price. So we left it at that because it's also interesting to see all of the range of possible results. And I think something that is very, very interesting of these two figures is that despite different national policies and greenhouse targets for different technological assumptions for these two regions in the world, the carbon prices show surprising similarities when we look at the median. In the US, it's around 410. In Europe, it's around 520. But most importantly for Europe is that we have a greenhouse gas constraint and not a CO2 constraint. So this is very likely that if we had a greenhouse gas constraint in Europe, it will be also around 500 to 600 US dollars per ton of CO2. So this was something that surprised us. We didn't expect so much agreement between both regions and across European and American teams, right? So that was kind of one of the first insights. So these are carbon prices. So we already talked emissions, where are the emissions going in both regions. We talked carbon prices. Now we're gonna move to changes in final energy demand, right? Of course, you can reach the net zero by having the same demand, just making it cleaner, or you can also reduce demand. As we all know, there will be a combination of both. We will reduce demand because we will use energy in a more efficient way, but also the energy will be cleaner. Here we have changes in final energy demand. So what we do here is each point is the difference between the national policy scenario and the net zero scenario. For example, in 2020, there are very few differences between both scenarios, right? But as we move to the future in 2050, there are large differences in final energy demand between the net zero and the MPI scenario, right? So everything negative means that there's less demand in the net zero scenario. And as you can see, in terms of exajoules, you have, for example, a median in the European Union of a reduction in final energy demand of 9 exajoules, or around 80%. Here is in percentage terms. And then for the USA, it's around 15 exajoules, or 32%. So there's a steeper reduction in final energy demand for the USA. This might be because the USA has way higher emissions, so it has a way longer path to go, but also because, well, the USA famously uses a lot of energy for their process because it has been traditionally an energy-rich country. So as an energy-rich country, well, energy is cheap, and thus the use of energy is not economically constrained, which is a difference with Europe, and I will assume also a difference with Japan. So the use of energy in Europe and Japan should be way more efficient than the USA. So, and that as a consequence, the reduction in final energy demand will be smaller for these two regions, right? With this reduction in final energy demand, you may wonder, well, final energy demand decreases. This is very interesting. Perhaps at the end of my presentation, I will show you the effects on GDP and consumption for both regions. It's around a decrease of 1 to 2%. Then we will say, okay, final energy demand decreases, but I'm very curious about how does the energy sources change and how does the demand across sector change? So what we did is this tree plot that I'm very proud of it, but perhaps it's a bit more difficult to understand than I would have expected. In the left-hand side, you have the national policies scenario. This is for Europe, right? And this is the final energy demand matrix. So everything black is fossil fuels. And as you can see, we divide them between transport fossil, buildings fossils, industry fossil, and non-energy fossil. So these are kind of the sectors. The yellow is electricity, and so on. And then you have the net zero, you have the reduction in demand of Europe of 9 exajoules, but you can also see a large reduction in fossil and a large increase in electricity. And this goes into the importance of electrification, right? So here we have an aggregate demand reductions. Fossil fuels decrease from 60.6% of final energy demand to 35%. Electricity grows from 27% to 44%, and biomass from 8 to 10%, and also an increase in hydrogen and synthetic fuels. So there's an overall decrease in fossil fuels and an overall increase in electricity mostly, but also in the use of biomass, hydrogen, and synthetic fuels. In terms of the sectors, there's not much change, right? You have that in 2020, the building sector was each sector was around 30%, and it remains so in 2050. So there's not many sectoral changes in terms of final energy demand. Something interesting for Europe is that their final energy demand in the transport sector increases by around 1 or 2%. And you will see that in the USA, it decreases. So this was one of the differences between both regions that we saw. We, of course, have the same figure for the USA. And it's the same intuition. We have an aggregate demand reduction from the MPA to the net zero, but also a big decrease in fossil fuels, around 25 hectajoules. And these 25 hectajoules were similar to the reduction of around 30% in Europe, an increase in electricity, an increase in biomass, an increase in hydrogen and synthetic fuels. So until here, nothing surprising. What it was very interesting for us is that the transportation sector in the US seems to have an increase in a decrease in final energy demand, while in Europe, it was an increase in final energy demand of around 2%. But the idea is that Europe have already a very spread out public transportation system and a very efficient use of their transportation infrastructure. So the room to decrease demand is way less than in the US, where everybody drives with a big truck. At least this is how we understood it. So until now, so there's the reduction in final energy demand. This reduction in final energy demand seems to be accompanied by a big reduction in fossil fuels, a large increase in electrification, and also some increase in biomass and synthetic biofuels. And I think you can see it way more clearly here. What we did here is that we show you the percentage change in several of the main carriers of final energy demand. And as you can see in both Europe and the USA, there's a very, very large decrease in what we will call traditional carriers. So we will have a large decrease in coal, gas, oil, and nuclear, right, for Europe and the USA. And on the other hand, you will have an increase on solar and wind, that this will be in line with the electrification, but also an increase in other type of technologies like biomass or hydro or synthetic fuels, and so on. Now, until here, and this was very interesting, the first time we sent the paper, we were very tired because of all of the coordination that we needed to do with all of the modeling teams to just get these descriptive results. But then the reviewers asked us, we want to see more interesting statistics than emissions or final energy demand. What if you talk about energy intensity or emissions intensity? Can you tell me something about this? So in the revision of the paper, we included some very interesting analysis of energy intensity. So what I'm gonna plot here, these are megajoules per dollar, right? And then I will plot you for Europe in the MPI scenario and for Europe in the net zero scenario, following USA in the MPI and USA in the net zero scenario, right? The first thing to notice is in 2020, at the start of the year, energy intensity of Europe is lower than for the USA, right? 2.5 versus 3.5 megajoules per dollar. And this just is in line with the fact that the USA, as I said before, has been an energy abundant region. So the idea is that as energy is cheap, you will use more energy to produce the same amount of economic output because energy is cheap, right? Well, in Europe, traditionally, well, after coal, energy is expensive. And as a consequence, Europe has better energy intensity. I will expect that Japan will have even a lower energy intensity than Europe. Then you have that the MPI, the national policy scenario, leads to around 1.5 megajoules per dollar in Europe and 2.03 megajoules per dollar in the USA. These are reductions of around 60%. Still in the MPA scenario, the USA has a larger energy intensity than Europe. But something that was very interesting is that net zero leads both regions to 1.5 megajoules per dollar. So in the net zero scenario, both regions reach the same energy intensity. And we didn't put this in the paper because this is just, there's no scientific reason behind it, but we believe that perhaps there's some technological frontier going there that teams cannot advance further than that. And that is because there are technological assumptions of all teams that in a net zero world, the most that we can get is 1.5 megajoules per dollar. So that will be energy intensity. And then, of course, we did carbon intensity. And it's kind of the same intuition. Europe MPI, Europe net zero, USA MPI, USA net zero. Of course, these are kilograms of CO2 per gigajoule. And of course, in 2050, the net zero, it will be zero because CO2 will be zero. And just by mathematical construction, your carbon intensity goes to zero or even to negative. Something interesting, in 2020, Europe and the USA over here have similar carbon intensity is something around 60 kilograms of CO2 per gigajoule. I think it will be a very different story if we talked 10 years ago, but the US has become significantly cleaner because of gas. Then we have in NPI leads to a reduction of about 10 kilograms of CO2 per gigajoule in terms of carbon intensity. So if we leave things as they are, we will have improvements in carbon intensity, and this is natural, right? We know that we have these very efficient new technologies like solar, wind, batteries that are substituting dirty technologies. Even if we don't push for a net zero world, these technologies are more efficient, and thus you will have a reduction in carbon intensity. However, this substitution of technologies, in our opinion, will take too long, right? Perhaps we will reach a net zero world in 200 years if we just leave the technological pathway, move naturally with the economy. But in the end, what we want is to push it. And so the MPA leads to that. And of course, the net zero leads to a carbon intensity of 0 for the USA and -3 for Europe. And you will say, what the hell a -3 carbon intensity means? Remember that Europe has the greenhouse gas budget constraint instead of the CO2 budget constraint. So in terms of CO2, it always reaches the negative terrain. And the next picture, and I think it was one that I was proudest that we did, and it packs a lot in just one picture. So I'm gonna explain it slowly because I think this is the most fun picture. What we have here is annual energy and carbon intensity improvement rates, right? So in the y-axis, you have annual energy intensity improvement rate between 2020 and 2050. This is an annual rate of improvement of energy intensity, how good we are at using energy to producing things, right? While in the x-axis, you have annual carbon intensity improvement rate. This means how much is the amount of carbon in an energy production improving, right? And what we have here in these dashed lines is the historical average between 1970 and 2010, if I'm not mistaken, right? So the idea is that we will show you results for the MPI scenario. Here will be the triangle and the net zero scenario in each model. So move with me. So the median improvement in energy intensity, this y-axis, in the MPA scenario between 2020 and 2050 is around 1.4 and 1.3% respectively. So in the MPA scenario from here to 2050, we're going to have 1.4% improvement in energy intensity in Europe and 1.3 in the USA. And the interesting question is, what has been the historical? So how good have we become historically using our energy resources to make production? And it's around 1.25%, right? So the MPA scenario is a little bit better than the historical average, but not much, right? But then when we go to the net zero scenario that is over here, so it will be all of these circles over here, the rate of improvement increases to 1.64 in Europe and 1.73 in the USA. That this is already significantly different from the historical average, which means that in a world without the net zero constraint, keeping our same policies, we will get a little bit higher energy intensity improvement rate. But in a net zero world, we really need higher energy intensity improvement rates. We need to use our energy resources in a more efficient way. But this is nothing compared to the carbon intensity, right? So regarding carbon intensity, the median improvement, so this will be the x-axis here. The median improvement in the MPA scenario is 0.9 and 0.7% respectively, right? So you have here 0.9 for Europe and around 0.7% for the USA. And then you will say, okay, what is the historical carbon intensity improvement rate? And that's around 0.25%. So already in the MPA scenario, our carbon intensity improvement rate is 3 to 4 times larger than the historical, right? And it was not surprising for us because all of these technologies, the green technologies, are by definition new. They have occurred in the last 10 years. And thus, as a consequence, even in the MPA scenario, we are having better improvements in our carbon intensity than before, where our only green technologies perhaps was hydro and sometimes of geothermal and biomass. More importantly is that if we go to the net zero scenario, so it's these lines here, the carbon intensity improvement rate increases dramatically to 3.3% in both regions. This is almost 20 times higher than the historical average carbon intensity improvement rate. So what all of these models are telling you is, okay, we're gonna reach net zero with a combination of improving energy intensity and improving carbon intensity. Both are there, but most of the improvement will come from carbon intensity, meaning that we will produce energy with cleaner sources. And this just makes sense because, well, there should be some not only technological but physical frontier to the efficiency in which we can use energy, while there's not such frontier in how clean the energy can be with the technology that we have, but especially with the technologies that we're planning to develop. So that was forced by us, by the reviewers, and we were very happy that they forced us to analyze this and try to make sense of the results in a more nuanced way. In the next round, what I want to show you is electrification in Europe. As you saw, the reduction in final energy demand comes hand in hand with a large electrification across sectors. So what I'm going to show you here is the three sectors: buildings, industry, and transportation. And then the orange line is the net zero electrification rate for that modeling team. And the black line is the national policy scenario, and the gray line is the electrification that the model is reporting in 2020, right? And what you can see is that the EU 2050 share of electricity, the median share of electricity across all models, because you have some models with around 30 to 40% and some models with more than 90. In the building sector is 72%, in industry is 51.7%, and in transportation is 34.8% of electrification in Europe. And this is important, and this is very important in the context of the American Energy Modeling Forum, because the name of the Energy Modeling Forum is High Electrification Scenarios in North America, and a lot of the work focuses on electrification, which will be one of the most critical sectoral shifts in order to reach the net zero that we require to be in line with the Paris Agreement, right? Then this is for the USA. As you can see, in the USA, we have way more models, and it's the same story. So this share represents a significant increase in electrification. Buildings have an electrification of 72%, very similar to Europe. Industry of 30%. If you remember the previous slide, industry in Europe is 51%. And talking with the industrial team of the Energy Modeling Forums, they were absolutely not surprised. And this is just because industry in the USA tends to be way more heat intensive than in Europe. So it requires higher heat that sometimes electric furnaces don't manage to provide. And then the transportation sector, around 29.5%, which is, again, very similar to the 34.8% in Europe. So there's a large share of electrification in both regions, right? Then, of course, this electrification comes hand in hand with a change in the power mix. It's not only that we're going to electrify everything, but still using the coal power plant, is that we want to electrify everything, but use renewable technologies. And all of the models move into that direction. This is the net zero scenario, the change in exajoules in each energy source for electricity, and then you can see the big change. So you have a general decrease in traditional technologies, large decreases in gas, large decreases in coal, decreases in nuclear, even decreases in hydro and in oil, and a general increase in new technologies like wind and solar. Very heterogeneous. Some, for example, some models rely a lot on solar in the USA, like ECMSMR, while others in a combination of wind and solar. And then you may wonder why there's this heterogeneity, and it has a lot to do with their constraints and their assumptions regarding the transmission network and how expensive it is to increase the transmission network, and also how fast can you increase the transmission network. So for example, with ECMSMR, their model can just suddenly increase the transmission network, and thus, well, solar is the cheapest technology because there's a lot of resources in the south of the USA, and that's why they just use solar, right? So as you can see, each model will have its caveats and its there's had been a lot of papers talking about the 100% renewables scenario, meaning countries in which all of their power will come from 100% renewables. And what we plot here is pretty much the share of renewable energy sources for the net zero MPI and the share in 2020. For example, Eurocalliop for Europe can easily reach 100% renewables in both the MPI and net zero scenario, while it has around 40% renewables in the share in 2020. The European Union median renewable share increases from 38% to 75% between 2020 and 2050 for the net zero scenario. For the MPI scenario, I'm sorry. So even in the MPI scenario, there's a large increase in renewables use. In the net zero scenario, the 2050 share grows to 85%. And for the USA is the same, but in the MPI scenario share is only 47%. However, the net zero value is closer to 80%. And yes, Masa, I'm pretty much finished. I'm in the thank you slide. I'm just gonna take advantage to discuss a little bit about, it will take me 2 seconds. We also have time series of gross domestic product and consumption. Another reviewer asked us, well, what is the effect on gross domestic product and consumption? And what we find is a decrease of around 1 to 1.5% in the gross domestic product of both regions in the net zero scenario, and a decrease of around 2% in Europe in consumption and 5% in the USA in consumption. And these results are surprisingly and, well, happily in line with the estimates of this NFTS, Association of Central Banks, modeling kind of the macroeconomics of climate change, this reduction of around 1 or 1.5%. And with that, I close. Sorry for so much information in so little time. And well, I'm open for questions if anyone has any.
Yeah, thank you, Luis, for such a comprehensive and a lot of work. I actually myself have been running with the Japan Model Intercomparison Project, or JMIP, and we actually we started this under the auspices of EMF, Stanford Energy Modeling Forum at 35, and we are now a bit independent, but I totally see Herculean efforts you guys have made, to make it possible. So yeah, and there are a few questions. Like one question is in the chat, but let me say one thing. You talked about the energy intensity of the economy, and you syndicated 1.5 megajoules per US dollars, and I checked maybe the constant dollar year is different, but it's like when I looked at my most recent result, it's like 1.2 megajoules. So
We have $2018.
What's that?
$2018 is
yeah, but in my case it's like $2010, so I cannot do the conversion correctly. But and the other thing is like quick
how much is it in Japan? Sorry,
what's that?
How much is the energy intensity in Japan? You were telling me that
1.2 in the net zero by 2050. So that's we are more energy efficient perhaps.
Yes.
And the other thing I would like to do, this is again the small confirmation, but so you talked about a very important like a technical difference between net zero and net CO2. So in your study, it was net zero GHG for Europe and net zero CO2 for the United States. And
Yes.
you hinted that the difference is about on the order of 5% emissions. Is that right?
So what we calculated is in Europe, the net zero goes into the negative terrain in a matter of 135 megatons, right? So what we compare is that we compare this negative 135 versus the MPA scenario, which was around 1,500 to 2,000. So it's around 5 to 10% if you compare it to the MPA scenario, this additionality. Because of course, you cannot compare this additionality with a zero because it's zero. You cannot really say what percentage.
Right.
But it's 5% of the MPA scenario, this additional 135. And this is in line with the Energy Modeling Forum. A couple of teams run greenhouse gas scenarios on the side in order to see how relevant they were. And the conclusion was the same. When you push greenhouse gases, you get kind of an additional 5 to 10% net zero with respect to MPI, right?
Yeah, that is consistent with our results. So I think roughly speaking, of course, the models are quite diverse. And also, like I just wanted to say, I like to do block figures for like electric building electricity, and I really appreciate it. I have a question, but I think I should give the floor to. I should pick up some questions from the audience.
Yeah.
So I didn't have time to read it, but so here's a question: do the American models consider CO2 equivalent for other important greenhouse gases like methane, or is it only pure CO2 emissions?
Emilio, that is a great question, and that was a reason for, I will say, internal fighting in the Energy Modeling Forum, because some modelers were really concerned about modeling net zero CO2, and they were saying what you were saying. They were saying, what about methane? What about other greenhouse gases? We need to integrate them. So what happened is, it was reached kind of an agreement in which all of the models reached net zero CO2, ignoring all of the other greenhouse gases. And then there was this additional exercise on the side of the models that were like, we really want to model greenhouse gases, that model a net zero greenhouse gas constraint. And then in the main paper of the Energy Modeling Forum, in the leading paper that was published 3 months ago, they discussed this a little bit. I will say we don't discuss it enough. I will say the USA, and I will say it would have been better if the Energy Modeling Forum will have modeled greenhouse gases, but it was just the decision in 2022, and that was the decision that we stayed with. So no, most models only CO2, and then some models have an additional scenario with greenhouse gases, Emilio.
Yeah, so actually, one point I would like to add is that this, I just sent the URL or DOI of your paper in the chat, but it's like a part of the special issue. There are a lot of ongoing parallel works, and there was a nice paper in Science which looked at the impact of Inflation Reduction Act using a multi-framework. So there are lots of multi-model research going on in both in the United States and Europe. So
yeah, the 3 to 4 papers already coming this month that has to do with the effects of air pollution of this net zero policy, some equity analysis, very interesting stuff. But all of this will be part of this special issue. Okay, let me answer to Stephanie. Okay.
Yeah, please.
So Stephanie says, given the CDR CCS technology is still in the development phase, I'm curious how the models might behave with the emission reduction target rather than a net zero. Do you still have insights of thoughts on this? Actually, we do have some results on that. I don't have them in the top of my mind, but there are some scenarios in which there were specific targets for emission reductions. I can check them out and see if they're part of the main paper. I don't have it in the top of my mind. But from right now, I don't really know how will they behave, because these models in which you only have an emission reduction target, they were only a few models that run them. In the end, both modeling forums decided on a net zero as the main target. Then some Japanese letter that I don't know what is your name, but I will read the question.
Asuka Sensei, yeah.
Asuka Sensei, okay, Asuka Sensei. I would like to know the reason why the future role of nuclear power differ amongst models, just cost assumptions. Oh, there's a lot of assumptions there. We, in both modeling forums, and I'm sure in the Japan modeling forum, one of the driving ideas is that we will let each modeling team assumes what they find sensible, or whatever assumptions, because we want to understand the range of possible scenarios, right? Talking with models, there are some modeling teams and some engineering schools that see a lot of promise in nuclear, and they have different assumptions about the cost of nuclear or the policies of nuclear. And I know models, for example, AnyMod in Europe, that just believes nuclear will become eventually more and more expensive. So nuclear is one of these technologies in which assumptions are very heterogeneous, so change a lot across models. What happens is that when one model can introduce nuclear substitutes some of the introduction of solar and wind. So it's become a green technology, but this really depends on each model. And I think this is the interesting part for policymakers, to see from this heterogeneity of models, to see that some of them are still betting from nuclear, while a lot of them are just betting for the new green technologies. And this is already an insight, meaning that even within the scientific community, we're not really 100% sure what the role of nuclear will be. Some people have very strong opinions, either on one side or the other, but if you see the results of the models, it's pretty much a 50-50 of people saying that nuclear will be relevant and 50% saying it won't. And this is kind of the beauty of these kind of exercises.
In the interest of time, probably we can take one question from Eamon. So
yes.
you can read it out. But so do you treat hydrogen power generation as a renewable energy option? Is that because you only deal with the green hydrogen, or is it going to be the most dominant one? Is that?
We discussed that in the European Climate and Energy Modeling Forum. When the models use hydrogen, they use green hydrogen because hydrogen tends to be expensive. So the idea is that hydrogen is just a technology that the models use to reach the net zero constraint, and thus they have to be fed by green technologies, right? So if you want to reach the net zero constraint, you want to use hydrogen, this has to be green hydrogen, right? That was the assumption. And when we look at the models, most of the hydrogen produced by the models, those models who produce hydrogen, not all of them use them, most of the hydrogen was green hydrogen. And so we decided to put it as a green technology. But there's actually an accompanying paper in the special issue in this, they look specifically at hydrogen. So there's a hydrogen paper in which they really go inside and they see of those teams that are reporting hydrogen, how are they producing it, where are they taking it? This paper, I believe, is still in the pipeline, but it should be out in 2 to 3 months in which they really go inside this hydrogen.
Yeah, I think it's over because it's getting a bit later in Mexico City. So yeah, and also I think so I'd like to wrap up and close. Sorry for not being able to answer all the questions, but I really appreciate your presentation, excellent presentation, Luis, and also a lot of questions from the audience. And thank you very much for that. And this is the first of the online seminar series we kick-started. So there are, like how you have seen, that there are a lot of interesting research happening in Japan and also in the United States, Europe, and also across the world. So we would like to showcase our own research as well as other cutting-edge research. That's the point, that the intention of this seminar series. And it was our great privilege to have Dr. Luis Sarmiento as our first speaker. So please join me in thanking him. So thank you, Luis, once again.
Thank you, Professor. Thank you very much, everybody.
Yeah, thank you.
Thank you. Ciao, ciao.
Yeah, so I will close the seminar. Bye-bye.